Need to double check. We're live.
Let me. Yeah, we're live.
All right. Hello, everyone, and welcome to Quadcast. I am your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome, everybody, to a brand new, exciting episode of Quirkcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode, and we'll get to them. So without further ado, let's get to it. So I guess, Tim and Mikey, this is an interesting question that we're tackling. Can physics ever be exact? And I think it's important for us to define like this question more appropriately. So I guess to start off, Tim, how do physicists think about the word exact? And what does that even mean from a
Great
physics?
question.
Yeah, and I think because physics is an experimental science, exact, should come with an experimental definition. It means that your theories spit out some numbers, and when you go measure them, they match up. And exact, I guess in practice, will mean that it's very, very close to be the same, and there's no known error, maybe other than some experimental artifacts. Of course, there's a little bit of debate on what's experimental artifact, what is the deficit of a theory, but if you ignore that for a little bit, that is what exactness should mean.
Okay. Mikey, do you want to add anything to that?
Yeah, I mean, I guess the more I think about it, the more it's like it stops becoming. It's really like a philosophical question. Like when you start to like actually think about what it means to be exact, right? Like if there's like a point in space whose like coordinates are like 0.1567, it's like a million decimal places, like x, y, like, and I shoot a dart, like there's a 0% chance that I'm gonna hit that exact. Like if it's, let's say, like it's like on the x-axis, it's like pi on the x-axis, like 3.1415, and pi on the y-axis. Like I'm never gonna hit exactly that decimal point number, right? That's just the nature of real numbers. There's an infinite number of them, and it you know yields an infinite number of possibilities. And the idea that you would hit exactly that one out of an infinite number is zero. So, I mean, this almost sounds like, I don't know, viewers might have heard of like Zeno's paradox, like the idea that if Achilles is racing the turtle can never win because it just has to like get half. I forget how the argument goes, but
I think it's Achilles can't win.
Yeah, Achilles can't win. Yeah, I actually forget why, but I don't know.
The argument goes that if the turtle starts a little bit up ahead, by the time Achilles catches up the turtle goes a little bit further. And then when he catches up again, the turtle goes further. And so it's like he'll never really catch up to the turtle.
It's so dumb.
I mean, it is, yeah,
Well,
I don't.
luckily, thanks to Isaac Newton, we know exactly how to take an infinite number of infinitely small things and make them into something finite.
Yeah. So on that note, I guess like how do like I guess to kind of give the crux of this episode, like how do physicists calculate these things, or what do they use? What's like the broad set of terms that we'll introduce in this episode of how they go about this? I guess Tim, I'll point this question to you.
Yeah, first I think we should clarify a little bit first. When we ask the question whether physics can be exact, there's usually a experimental and theoretical component. Experiments are not perfect, measurements are not perfect, so that of course will create inexactness. Let's ignore that for now. Let's focus on the theoretical aspect. Let's take a theoretical theory. So where would this inexactness come from? Where do we ever get an exact answer? I think so. In physics, you usually start with some theory. You propose some idea, but
Wait,
that
so just to be clear, so you're talking about like the distinction between theoretical uncertainty and experimental uncertainty?
yeah, sort of, because I want to separate out. Oh, maybe you just aren't doing your experiment perfectly. You
Yeah.
know, let's just ignore that for now, because I think that's another topic of discussion. It has to do with experimental physics. Let's not focus on that, right? But in theoretical physics, even when physicists build a theory, a lot of times the theories are very complicated. It's not just like, oh, simple math, 1 + 1 = 2. Let's say when you do 1 + 1 = 2, that's an exact answer. You know, 1 + 1 is not 2.1, it's not 2.2, it's 2. Yeah. But in physics theory, when you write down some kind of theoretical model, sometimes you don't even have that, because the theory is so complicated. We don't even know how to calculate things. And this is actually true even in a computer, right? When you try to calculate something in a computer program, like let's say pi. What is pi? You can't quite get all the infinite digits, you know, unless you draw a perfect circle in some ways. So even from going from theory to just calculating a number, there might be uncertainties or approximations that come up because you just couldn't do the calculation appropriately. So this is what we're talking about here today. And it turns out that this level of uncertainty is actually, you can argue that maybe it's a practical problem, but at the same time, it's also actually a theoretical problem we'll describe later. So that's where it gets interesting.
Yeah, and a philosophical problem.
Yeah. So let's break it down. So, I mean, theory has to relate to experiment. I know you said let's forget about experimental errors. So let's say you could do a perfect experiment. So you have some kind of system that you're trying to essentially measure or get certain quantities out of it. Could be an electron, could be a system of particles and whatnot. So you create some sort of disturbance. You throw a photon at it, throw other particles at it, and it creates this disturbance. And you want to compute something from that. I would imagine, like, if you want to measure, say, the charge of an electron or the mass of an electron, you need to interact with it in some way. So you need to disturb it in some way. So I guess, like, how do physicists think about these, like, disturbances and how they relate to the theoretical framework of physics?
Wait, maybe we get back, like, I don't know if this is a good idea, but like I have this idea in my head about like a little bit more abstract. Like say you had an experiment that was perfectly accurate, and you're going to like put in some chemical ingredients or whatever, and you know you're going to measure like how many like, you know, molecules of like some chemical comes out, and you know the answer is 2, right? So if your theory is right, then your theory has to predict 2, right? And as Tim was saying, like, maybe your theory is really awesome and it's like really simple and easy, and it tells you, oh, it's like 1 + 1 is 2. That can happen, but we never get that lucky. What often happens, you know, and there's many different ways to express the number 2. You can express 2 as 1 + 1. You can express 2 as 0 + 2. Another way to express it is as 1 + a half + a quarter + a 16th plus, you know, an infinite sum. Yeah, some viewers might know this is a geometric series, but you can actually prove mathematically that if you take like 1 + a half + a quarter + a 16th, you're adding an infinite number of things together, but you're getting closer and closer to the answer, the exact answer, quote unquote exact answer, with every single piece of effort that you put into it. And that's kind of a good analogy, I think, for like where we are with physics right now. It's like we know how to get a lot of answers like that, where in order to get, we believe that this calculation represents the exact answer, but to actually compute the exact answer would take an infinite amount of work. If that makes any sense.
I think we can kind of go back to Sahiwa's question and take an example, right? Let's say you just take 2 electrons and you just push them together and see how they move apart. Even this sounds very simple, right? Even in this case, it turns out that we'll describe later, quantum physics means that this process actually is very, very involved. So you can't just calculate it from nothing. You have to start from somewhere. And that somewhere usually is, well, let's say you're smashing electrons together at energy 500 units. Let's say you're doing that. What physicists do is, well, it's very hard from nothing. But what we can do is, if you have data from smashing electrons at energy 400, you can maybe extrapolate a little further to see, well, what happens at energy 500. So this is a very simplified version. But, this sort of extrapolation, and I think we can introduce this technical term here. The way to do this extrapolation is called perturbation theory.
Mm-hmm. Okay.
It's like you start from somewhere and you just explore a little bit around there.
Yep, exactly, yeah.
And you hope you can get a global picture, but yeah, often not.
Okay, so I guess when you talk about perturbation theory, what you're referring to is like when you basically disturb the system in a small way, and you're hoping to get something, I guess like more general about the system,
Yeah,
like beyond
yeah.
the small disturbance.
Like say I have a soup bowl and I have a marble sitting at the bottom of the soup bowl, right?
Okay.
I know the physics of how that works exactly because the marble's just sitting there. The physics is that it just sits there. And if I want to know exactly everything about how this marble could move, the first thing I would do is just poke it a little bit and just see how it moves a little bit. And then I would just get a sense for how it moves and then try to poke it more. Because, the more I hit it, the harder I hit it, the more unpredictable and chaotic its motion becomes. So if I wanted to take a strategic approach to understanding the behavior of this thing, I would start with, small taps.
I see. Okay, so if you have some system and you want to understand some things about it, you would basically create a small disturbance, and then you would probably increase the size of the disturbance. So, yeah. So
let me say this is purely due to a lack of our own imagination. This is just the only way that we know how to attack a problem. We're not happy with it. This is just the only way we know how to make progress.
Yeah.
Oh, go ahead, Tim.
Yeah, and I would say actually a very good analogy is weather system, and because it turns out that the fluid dynamics equations share some similarity with the equations in particle physics. So the situation applies in weather patterns as well.
I see. So okay, so like Mikey, how does this like small disturbance relate to this infinite term thing you mentioned? Like, you mentioned there are different ways of writing two, and it's some way of writing two. So yeah,
right.
can you give the relation?
Exactly, yeah. So like for example, suppose there's some theory, like suppose again go back to like the marble at the bottom of the soup bowl. Suppose there's some general theory that just tells me like no matter how hard I push it in which direction, this theory will tell me exactly what's going to happen. And I'm trying to discover this theory, and the way I discovered is by starting with like small pokes, and then progressively getting harder and harder and harder to try to get a sense for this. That's kind of like expressing two as this infinite sum. Like one is half of two, so you get most of it there. You get a big chunk of your answer there, and then you add another half, and you get another big chunk there, and then you get closer and closer to your answer. Like we say, infinitesimally or asymptotically close to your answer. And that's kind of the way it works. Like if I tried to figure out how the general theory for how this marble moves just by poking it, I would get asymptotically closer and closer to the answer the more I poke it. And that's like each term being added to the sum, like each new piece of information being added.
Yeah, I would say if you go to the weather analogy, this is probably a little more realistic now. And we know that weather system is extremely complicated. Like it's really hard to predict the weather in a month, right? It's really difficult. Even in the next few hours, depending on where you live, the weather could be very unpredictable. So how do we predict weather? Imagine you have no data. You just have some idea on how the atmosphere of the Earth moves. Theoretically, you may be able to predict something, but that's almost impossible, yeah? Because you just have the shape of the Earth, all the location of the air molecules. That's an impossible problem. So what people will do is they do perturbation. Be like, hey, we know what the weather is right now. We can kind of look at the wind directions and see what's going to happen and see where the hot air is moving, and then extrapolate.
It's not that different a second later.
Right, yeah. So we can predict, hey, maybe what's gonna happen an hour later, right? So we'll get some answer. But if we want to do, let's say, calculate the weather in a day, you might have to do this step multiple times now. Like, oh, what's gonna happen in an hour? Well, we can extrapolate to there, and then again and again and again and again. So each step, there's more complications now. Like in the next seconds, maybe a butterfly can flap his wing, create a little turbulence, and the next 10 minutes, the turbulence gets bigger. Maybe, and then in the next day, maybe it will spread somewhere else, and maybe at the end of the day, it will create some enormous hurricane, right? So you see that each term can progressively get more and more complicated because you got to incorporate more and more information to kind of do this extrapolation.
In fact, that's been proven, right? So, like, if we go back to my marble at the soup bowl thing, you can actually show that you can never learn the entire behavior of the marble just by poking it, like, softly. There's certain behaviors that you can only access if you poke it hard, and you'll never see them if you only poke it softly. So this idea of like trying to get the entire picture just with these soft perturbations is demonstrably, provably what fool's errand.
I see. I mean, but you mentioned there's like an infinite number of terms associated with it. So wouldn't you be able to like capture everything about it if you were able to put in an infinite amount of work?
I believe that's not true. I believe they've shown that there are certain results that you can't get.
Yeah.
You can't reach it just with this approach. There's certain truths. It's almost like if you think of theory as like a space, like we're restricted to a kind of a small piece of it. Like we only understand how things work when things are not violent.
Yeah.
Because when things are not violent, then we can kind of do these small pushes and kind of explore the system gently. But when things get violent, the whole picture changes, and none of what we know really applies. And this is like a whole part of physics that we don't really understand, like the physics of violence.
Yeah, and I would say for the weather analogy, like an example would be like tornadoes. Like
yes.
You perturb your system a little bit. The next seconds, the wind might move a little bit faster, and then faster yet, and then the wind patterns will change. But then at some point, catastrophic things happen. There's a vortices that gets created. The wind starts twisting around. When that happens, we believe that probably some of the mathematical machinery just breaks down, and it's just no longer.
Well, it doesn't just break down though, because these structures have their own very simplistic descriptions, which means that it's not. It gets complicated and then it gets simple. Right? Like the storm is so complicated, and then suddenly it's a tube. It's crazy. We don't understand how these kinds of transitions happen at all. I mean, when I say we, I mean we as physicists.
I think if I'll refer to the listener to one of our previous episode on the space of theories, and it's almost like at some point, once you move too far away from where you are in the space of theories, you just jump into another regime, right? And in the case of tornado, if you poke the weather system hard enough, you're going to create a monster object, and that's you're no longer in the space, at least conceptually, where you started with. It's categorically different now.
Yeah.
I mean, like if I were to give a simpler analogy, would you say that if you take like water, for instance, and you heat it up really like, very lightly or like less heat and just kind of just like increases it, but it's still liquid, versus if you like keep increasing the heat, it'll eventually turn into vapor, which is something you wouldn't be able to predict from slowly heating it up.
Yeah, exactly. I think so. Yeah, that's some. Okay. I think phase transition can be categorized as something that's you don't exactly see using just perturbation theory. I think you have to go a little beyond that. Yeah.
Yeah, definitely. Yeah.
That makes sense. So perturbation theory is a theory in which you use it to describe small disturbances. How does this appear in quantum mechanics? Where does this show up?
Yep. So now this is where it gets interesting. So the analogy kind of is similar, but it's a little different. So where in the weather pattern analogy, you started with the weather today, and then you try to predict the weather later. What's the starting point in particle physics, right? There are actually many different starting points. In particle physics, at least quantum field theory in general, it's not a it's not a well-defined theory. So the starting point is just whichever is most convenient. And most often, the starting point is a trivial theory. Like, for example, you can have a particle moving around, not doing anything. And then you say, well, what if I just turn on a little bit of probability where this particle can get a kick, let's say out of a photon, or it can hit another particle and change directions. You add in that interaction and you try to dial it up, right? And then this is the extrapolation you're doing. What if I increase my interaction a little bit, a tiny bit at a time to see what happens? So I think that's the most common form of perturbation expansion that we do in particle physics, but there are others.
Yeah, and I think that's a good example because it highlights what happens when things get crazy. Like you said, like when interactions and forces are weak, we can kind of play this game where we can understand the system by pushing things around softly and probing the system gently. But when things get really violent, the structures literally change. Like particles stop being particles; they start stretching out, and your whole description of the system starts to change. And yeah, and perturbation theory stops working. This idea of gently pushing things does nothing to tell you how like a violent, catastrophic world behaves.
Mm-hmm. But I guess if it it seems like this is one of our strongest tools. I'm wondering where does it work before we discuss like where it
Wait, it's
doesn't
not our
work.
strongest tool. It's actually a tool that we've relied on for like 300 years, and that everyone wishes we could get past, but we can't.
I
And I don't
see.
know, maybe we get to, like so. I think it's like we're trying to think of yesterday of like examples of times that people have gone beyond this. Because it's a tool that we rely on. This idea of, oh, we can build up our answer, we can get the exact truth by building things up incrementally and slowly get there.
Yeah,
But once in a while, people find a way to get at the exact truth, and there's no like systematic way of doing it. I don't know, other than just human genius, I
Yeah, well,
guess.
let me just say a few words about this general principle. Like, where is it used? It's actually used everywhere. Like weather patterns, we use probably a lot of perturbation theories. For example, we can also do perturbation theory to look at gravitation.
It's the only trick we know.
Yeah. Like, for example, NASA, when they predict orbits of different planets, they almost definitively use perturbation theory. Yeah. You can use perturbation theory to correct timings of satellite. It's pretty much used in engineering, and this general principle is just
we don't know any other way of doing things.
Yeah, and let me just say that this way of organizing things is also very natural. You start with something, and then you add up the corrections. So that's why when you talk to physicists, oftentimes you hear these things like, oh, this is a leading order effect. This is just your where you're starting from. And the first order term is, oh, there's a little bit of correction. And the second order term is supposedly a yet smaller correction, but the next term in your perturbation, and then third order, fourth order.
Let's start simply. If I'm trying to make a circle, I can't find a circular rock. I'll find some like square rocks. So I'll chip off the corners, and that's the first term. And then I'll slowly smooth it out until it becomes a circle. It's like this iterative process. That's how we operate.
I see.
Yeah. That's perturbation theory.
Yeah. So can you quickly just describe, like, I guess in particle physics, where this has been successful? Because if we've been using it for so long, surely it's led to some successes.
No, it's been successful everywhere it's been applied. That's why.
Okay.
And we become so lazy that we only we just rely on it because it always brings good results. Like we can always get almost the exact answer with it. So no one has even bothered to really spend much time thinking about alternatives, except for a few people who have come up with some things that could be argued as exact answers, but it requires like a wild amount of creativity. There's no systematic way of researching this. It's just literally pure
I
human
would
genius.
I would say, although this level of success you can attribute to the state of the world right now, because the world we live in, as we repeated many times before, we live in a very low energy world where interactions are not crazy, and the interactions are manageable. Like when I move my hand, I don't saw a nuclear reaction. Like nothing crazy happens. And because of that, because the energy exchange in different processes, the interactions are small enough. This perturbative expansion will give you reasonable answers. Like we're not starting tornadoes every day. And in fact, where it breaks down, we see it, right? Like we still don't know how to predict tornadoes. Weather patterns are very, very hard, and it's precisely for these reasons.
Yeah. We don't understand how turbulence works. These violent phenomenon are beyond our predictive ability.
But I would say similar things do exist in physics. You could have very violent. Maybe violent is not a good word, but like
not chaotic.
Yeah, like some sort of transition in your theory where you're just like, whoa, like this is very different from perturbation theory. In fact, we actually do see that a lot, and a lot of times we're just kind of like, well, what do we do about it? It's hard.
Yeah, that makes sense. Let's
for those people who know Ed Witten's name, Ed Witten is famous for being one of the very few physicists who came up with a framework for coming up with exact answers.
So I guess I want to be more specific and describe like what problems in particle physics you like just completely fail when you use this approach.
Well, nothing completely. Well, okay, maybe probably some things do completely fail. It's hard to think of something that completely fails. It is a really, really good idea, and it's a really great strategy, and it works for most things. The times when it fails are not like, it's not like crucial to the survival of humanity, but it's crucial to like our fundamental understanding of reality.
I would
Tim probably has better examples, but
I would say when the theory starts giving you answers that don't exactly make a lot of sense, you start to know that hey, something's going on. For example, let's say you do a calculation, like actually this happens. Let's just say it now. This happens for the strong force, for example. Let's say you gather some quarks, have them interact. Yeah, you might do a calculation, and your starting point maybe you get an answer that's 1, right? And now you do this expansion. Maybe you get 1 plus 1. Okay, that's not too crazy. And maybe you go to second order, you get 5. 1 plus 1 plus 5. You're like, whoa, hold on a second. These terms are not small at all. The next term might be minus 20. You're like, well, that's crazy. Like, the answer might just become kind of nonsense now. You might get something like 1 plus 1 plus 5, minus 20, plus 100, minus 1,000. You're like, well, that's nonsense. Like the perturbation expansion will tell you that something's wrong. And it turns out that for the issue for the strong force is because the interactions are very strong. So your assumption in the perturbation theory is wrong. You don't have a system where the perturbation is small. Perturbation being the interaction. The interaction actually is very, very large. That's a feature of the model. And that's why you cannot use perturbative calculation to predict, let's say, the mass of a proton or the mass of a neutron. You can't do that. So, like, this is an exact, or you can't exactly tell me how protons form. Like the probability of them forming. Like this is a real life example where perturbation theory just doesn't work. You have to find an alternative.
That makes sense. So what you're saying is that one fundamental assumption of perturbation theory, in order for it to work, is that like the disturbances are small. I mean, in other words, like the interaction is small itself.
Yeah.
So things like maybe electromagnetism or maybe
the scenario has to be non-violent if you want an answer.
That's fair. What about gravity?
Gravity
is really cool.
Yes.
So why work?
No, when we're this is like a big misconception when we're talking about non-violent scenarios. Our quantum theory of gravity works great.
Oh.
So it does break down when gravity becomes strong. Once again, it's the same idea, and one of the classic example when gravity gets strong is a black hole. So when gravity becomes very strong, you create a black hole. You know, like for example, we don't really know the process in which a black hole form.
Yeah.
And when you deal with a black hole, you all of a sudden you have to change your mathematical description. I mean, you can also modify the starting location.
Same thing with quarks. It's no different, right? That aspect is no different from
Right. Yeah.
quarks.
Yeah. When the forces get strong, perturbation theory will break down. Of course, you can modify your perturbation theory to maybe take that into account, and there is some success for that. Like maybe your starting point can be a black hole instead of being nothing. Then you can go somewhere. But like
rearranging chairs in the Titanic.
Yeah.
No,
All
but
right.
I mean, yeah, I mean, but like, I don't know. I think all this closing argument. I don't know, not closing arguments, but like,
Yeah,
I
yeah.
think the point we've been getting at right now is we've been taking the same approach to physics for a long time, and a few brave souls have made strong attempts to go beyond it. And yeah, I think that's where things need to go.
Yeah. Is there any like quick teasers that we can give of like what people have done to go beyond? Just
Oh yeah, we could give a long teaser.
just something. It doesn't have to be too long, but yeah. Just throw out a few things of what you like.
I mean, I guess the use of topology. So, like, I guess I don't know, people who know Ed Witten is famous for like incorporating topology and showing that it has like a large role to play in understanding physical phenomenon.
Mhm.
And topology is like, oh shoot, I'm gonna butcher this. It's I'm gonna spend a lot of mathematicians. I don't know, like because from a physicist perspective, topology is just like a dumb. It's like a way to reduce every physics problem into a counting problem.
Okay.
And when you're dealing with integers, we don't have this problem that we talked about before, where it's like, oh, like this answer is like 2.6934567. Like, oh, like has to be exact, right? The answer is 2, and your theory says 2, then you got it exactly right. And Edward's introduction of topology into physics just created this entire flurry of research into results like this, where all these integers started becoming important all this.
Yeah, I would say topology is a you know, using topology in particle physics is basically focused on aspects of a like it's like stripping down all the fluff of the theory, and you focus on parts of the theory that are resistant to perturbation. Like like technically, the topology of something does not change if you perturb it. And like a famous example is like a donut. You can imagine you made a donut out of clay, whatever. You can you can slowly shape that clay, as long as you're not breaking it, into a teapot or whatever. Then it's exactly the same, right? Like a in some topological view, a donut is the same as a teapot, as long as they have one handle. And you can do the same thing with particle physics. You know, a theory, you can maybe like imagine the theory is kind of like a clay. You can mold it and simplify it until there's not much left. It's really bare bone. And when that happens, well, the theory has become so simple that you don't even need perturbation theory. You can just get an answer. The answer might be like 5, and that's it, right? So that's one way you can sometimes get exact kind of topological answers. Yeah.
What are some other ways?
Nima.
Well, another way, I would say the most practical way to overcome this is through computers, right? It's just brute force calculate something. Like in the example of tornado, people have tried to just, maybe you can try to simulate weather pattern, just throw a bunch of pretend air molecules, see what they do.
It's never been successful though. Like they try to do tornadoes, they try to do the plasma fusion. My friend's dad does like something called gyrokinetic particle simulations, where they try to like do classical simulations of like atoms. It doesn't work. It doesn't work.
Yeah, but that's the thing, So perturbation theory is a generic tool to handle these situations. The alternative generic tool is just through simulations. And it's true that simulations are very hard, but we have had some success. So for the strong interaction, we have what we call lattice quantum chromodynamics simulations. These are very expensive calculations done on supercomputers. It's very, very, very hard, but we have some success to verify, let's say, the mass of a proton, to see that it sort of agrees with theoretical predictions. But
it showed us a few surprises too, like certain things we thought, oh, this was the answer for perturbation theory, and then we do a simulation, like, oh yeah, it's a little bit different.
Yeah, like also these simulation has, like sometimes so it has happened in particle physics that you have a theory, let's say there's some properties of some particles decay, and it doesn't match up with the experiment, and then when you see that, you're like, wow, hold on a second, is it because so there's a few possibilities. Is it because my experiment is bad? That could be. Is it because my theory is bad? Well, that could be. But when these processes, let's say, involve the strong force, well, it's hard to verify because it involves non-perturbative stuff, right? So you're like, well, shoot, is it my experiment that's bad, or is my theory that's bad? If the theory is bad, that's very exciting because that means there's new, we have new discovery. So people have spent a lot of time running lattice calculations, these non-perturbative calculations, and I think that some of the results are that, it actually agrees with the theory, and it's
most of the time it agrees exactly. Once in a while, if there's some surprises where we knew we were uncertain anyways.
Yeah, I think that's what
Nothing hate on QCD people.
The muon magnetic moment is one example. I mean, it's technical. I don't want to get into details, but this calculation helps. So I would say, computer simulation is probably the other angle, the other angle of attack, but it's not elegant at all. It's like very ugly, basically.
Gotcha. There's an audience question that came in, which is, how is this disturbance done in modern physics? Is a physical system literally perturbed, or is it something more abstract?
Oh no, literally, like you take your theory, like let's say I have like a theory of like a bench, and I wanted to like simulate what the vibration. You just like put in a term, like a little term that just, I mean, I don't know, maybe I misunderstood the question, but you can do physical experiments or theoretical experiments, but it really feels the same to me. You really just,
I mean, it is more abstract, right? Like the kinds of expansion can be really abstract. For example, you can in condensed matter physics, I think people have thought of 3-dimension system as a perturbation of 2-dimension system. They think of 2 plus 1. 1 is being like these are some of the craziest stuff that people have tried, right? Like maybe 2 plus 1. 1 is the perturbation to 2, right? This is pretty abstract. And also in the strong force calculation, because that in quantum chromodynamics there are 3 types of color, and you can expand on 1/3. 1/3 people think of it as a small number. So it's really kind of wacko. You basically you pretend that 3 is infinity, and then like 3 is a little bit.
That's how desperate we are to get answers.
Yeah. So 3 is infinity. so 3 is close to infinity, but not quite infinity yet. So you can expand on being infinity, but not infinity. If that makes sense.
It's way closer than 1. That's true.
Well, I'll top you guys by saying in a condensed matter physics class I took, we assumed 1 was infinite. So.
Oh, that doesn't make sense.
I mean, yeah.
3 is at least bigger than 1.
3 is bigger than 1. Yeah. 3 times bigger than 1.
3, I believe 3 could be infinity. I can't believe 1 could be infinity.
1 is bigger than all the numbers less than 1. So we'll roll with that. So we're almost at time. So I wanted to give you guys a chance to, leave the audience any words of wisdom that perturbation and non-perturbative techniques have taught you.
I don't know. it's kind of weird. Like, I don't know, when I was in physics, like it was so rare to get like exact answers. And the few people who were able to get exact answers became, famous. They became, gods in the field, like people like Cyber, Witten, people like that. Became famous for being able to get like exact answers. But yeah, there's just no general framework for doing it. Like every time someone does it, it's through some just shocking act of creativity. And so it
Mm.
feels like there's this whole sector of the universe that we're not really privy to because we only know how to explore a very small degree outside of our own comfort zones. I don't know, maybe that's an analogy for
Yeah.
something more. Maybe not.
I feel like, yeah, in my mind, I feel like perturbation, the way perturbation theory work kind of really works with the way human thinks about things, like whenever something happens, we always prescribes a little bit of reason. Like for example, well, why did it rain today? Oh, because there were some clouds. There's condensation. Like it's like this step-like process. One thing happened to the next, and it rained. And
Markup, yeah.
yeah, and this is kind of very very much the spirit of perturbation theory, right? You take today's weather, you add a little bit of this, and then this happened, and this happened, right? And this way of thinking has guided us very well in our lifetimes, in most of humanities, right? But it's pretty clear that the universe has situations and phenomenon that is not that. That you cannot just take that you can just break it up. You cannot just break it up and then sum up the parts, right? The phenomenon that where the sum of all its parts is greater than just the parts themselves. And it feels like, there's probably still a lot of physics still left, and we just don't really don't even have a good handle on some of these things.
And this is like the creation of the universe stuff. That's where all the violent stuff happens. These are the big questions.
Yeah, and maybe we haven't talked about some of the emergent stuff. Maybe, for example, AI could help us get the simulations better, get down those answers better. Or maybe, I don't know, in the next millions of years, maybe our brains can evolve to take information more holistically instead of in this perturbative fashion. But it feels like, it feels like this is not just a practical issue. There's like a fundamental issue about how computations are done, how we make predictions.
Yeah, I mean that's in my mind very optimistic, Tim.
This is the frontier.
More optimistic predictions I've seen from you.
Or I guess the pessimistic version would be that there are just things we'll never be able to know. It's just
laziness. No, it's no. People have proven that with hard work we can get beyond it. It's just we as humans we just
Yeah. Well, so on that note, I want to thank everybody for joining us, and we'll see you all next week.
all right. See you next week.